So this is the second, what should we call this? Lecture, talk, discussion on power series. And now we will do a problem. The instructions are find the values of x for which the power series summation n equals 0 to infinity x to the n converges. So I'll pause for a moment as you write this down. Now the important thing is to do the examples in order. They start out simple, but as we progress, the examples will become more and more complicated, each one building on the previous one. And if you do it systematically, even the more complicated examples become simple. So this was our first example, and now we want to determine where this power series converges. So it would help to do a quick review of geometric series, because this is actually a geometric series. So let's do a review of geometric series. Now this was in a previous series section. It was one of the first series that we looked at. Recall geometric series. So how did we define a geometric series? A geometric series has the form summation n equals 1 to infinity a r to the n minus 1. And it looks like this: a plus ar plus ar squared plus ar cubed plus dot 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 forever. And the first example we looked at in geometric series was this: n equals 1 to infinity 1 over 2 to the n. And then we applied the geometric series test. I'm going to write it down if you forgot about it. Geometric series test. If 0 less than absolute value of r less than 1, then the geometric series summation ar to the n minus 1 converges to a over 1 minus r. We write that it's equal to a over 1 minus r. And if absolute value of r is greater than or equal to 1, then summation n equals 1 to infinity a r to the n minus 1 diverges. So how would we tackle the convergence or the divergence of that first example here, summation 1 over 2 to the n? Well, first thing to observe is that 1 over 2 to the n is really this, 1/2 to the n. It's the same thing. And then in order to get my a and my r very clearly and put it in the form of the geometric series summation a r to the n minus 1, I'm going to factor out an half, and I have half to the n minus 1. So this is my a, and this is my r. R is half, so this series converges. This series converges, and in fact it converges to a over 1 minus r, so that's half over 1 minus half, and that is equal to 1. And we write summation n equals 1 to infinity 1 over 2 to the n equals 1. That's a really interesting thing if you think about it, and we talked extensively about this idea that you're summing up an infinite number of things and then you're getting the number 1. That's a really cool thing. Now what if you started with 0? N equals 0 to infinity 1 over 2 to the n. So that's equal to, well, just plug in what 1 over 2 to the 0 will be, and that's just 1. So you have 1 plus summation n equals 1 to infinity 1 over 2 to the n, which we just did. So that's 1 plus 1 equals 2. Now, how does this connect to our example of power series, which is right up here, summation n equals 0 to infinity. So we're done with our review of geometric series. So let me draw a line. Let me move this up here, try and fit some of this on one page, and draw this line like this. While you're finishing your notes, I'm just wasting some time here. So let's look at example 1. Summation n equals 0 to infinity x to the n. Now we already said that in this case, c is equal to 0, right? And instead of having a specific number like half to the n or 1/3 to the n or 7/4 to the n or something like that, you just have x to the n. Well, by the geometric series test, this series converges for absolute value of x less than 1. Right? Absolute value of x is less than 1. Here, x takes the place of r. And what does that mean? Absolute value of x less than 1 from pre-calculus is -1 less than x less than 1. And it diverges everywhere else. So we can actually draw it out now. Draw what we will call the interval of convergence. Let me draw a straight line here. So 0, 1, -1. And it converges on this interval and diverges everywhere else, diverges outside the interval. This is called the interval of convergence. So let's put that in red. This is called the interval of convergence. All right? And the radius of this interval is called the radius of convergence. It is 1 over here. Just moving this a little bit over here. Alrighty. So the interval of convergence, we should call this sort of like an answer to our question, is where does this power series converge? Answer, interval of convergence is -1, 1. Radius of convergence r equals 1. See, this would be the radius of convergence, the highlighted yellow portion. Something to note that we will talk about in the next example is that the power series always converges at x equals c. Over here it's 0, so it always converges at 0. Why? Because if you put x equals c in the power series, you just get 0. So nothing to it. It'll always converge at x equals c. And in terms of the domain that we had on the previous lecture, this is the domain of the function, the sum of the power series is -1 to 1. We'll just call it interval of convergence. So let's review this lecture. I'm not sure I like the word lecture. I need to come up with a different name for what this is. It's like the whole thing would be a lecture. You know, the introduction and then examples 1 to 4, 5, the whole thing would form one lecture. So I'm still talking with my hands, even though you can't see me. So we did so the question here is find the values of x for which the power series x to the n converges. We reviewed geometric series because this is really a geometric series, and the solution actually ended up being very short comparatively. It's actually the only one that's so short. And it just came from the geometric series test. But the important thing is we learned a new word, a new phrase, interval of convergence. And what is that? It's where this power series will converge. And the radius of this interval is called the radius of convergence. All right, that's it for this segment. I'll see you in the next one.